Yeah.
But then I kind of don't feel like writing cover letters.
You don't feel like writing cover letters?
No.
Well, despite what the clock on the wall is saying, which it looks like it got messed up again, but I think it's 10 o'clock. I think it's about time to get started here, so I'm gonna go ahead and do that. Just wanna welcome all of you to another week. We are officially on the downhill side of the semester now. I think we're a little past the halfway point, so we're making it. Hope that you guys are feeling okay about everything. Don't forget, we have a midterm 1 week from right now. So next Tuesday, it's going to cover all of chapter 4, all of chapter 5, which we've completely finished, other than maybe some homework questions today. And then the first part of chapter 6, the first section, I should say, of chapter 6, which I'm going to be talking about today. That'll also be on the exam next Tuesday. As you know, there's a resources folder in Canvas that has sample midterms, practice problems, some video for a review session, all sorts of things that you can be doing. My goal is to try to get us done with like all the homework in the next 3 days, basically. So there's an assignment due tonight, which I'm going to help you with today in class. And there's also an assignment due on Thursday that I am also going to help you with in class. I really would like to give you the entire weekend to kind of be getting ready for the exam. I am going to be putting together a little extra credit quiz, just like I did for the first exam, to help you kind of practice one last time and submit something. I'll only be giving you at most a couple of days to work on that. I don't know exactly when I'm going to send it out, probably towards the end of this week, and I'll let you turn it in sometime over the weekend. But you can just kind of view that as part of your studying, right? That's kind of just part of the studying that you'll be doing for next Tuesday's test. Of course, there won't be any homework due as you're getting ready for the test. You'll just be focusing on that. So that's kind of where we're at with everything. I kind of tried to give you an overview of that also in the email over the weekend. Does anybody have any questions before we kind of dive into this material today? So I will sort of backtrack to that homework and give people a chance to write some more problems down if they need to in a little while. But what I'd like to do first actually is just keep moving forward with this chapter 6 material so that we're ready for the homework that you're going to be working on for Thursday. So I'll pick up with a quick recap of where we left off. Again, this was 5 days ago. Just at the very end of class last Thursday, I finally had a chance to start chapter 6. And I didn't get much further than just kind of the basic definition that I've put back up on the board right here. We're talking in chapter 6 about linear transformations, right? So these are just functions, right? Mathematicians love to think about functions, inputs and outputs, right? But in the context of Math 250B, the inputs and outputs are going to come from vector spaces. So V and W are any of the vector spaces that we've looked at up until now, right? Could be polynomials, could be matrices, could be functions, could be traditional vectors with slots, could be anything really. Any example of a vector space that we have. And what we're going to be interested in is not just any old function that would be sort of erratic and impossible to describe. Rather, we're going to be mostly interested in functions that are linear. In other words, they're linear transformations. And what I mean by that is that these functions, in addition to having inputs and outputs in the two vector spaces, the functions need to respect the vector space operations, right? So of course, in a vector space, we have two main operations, which we've been talking about now for several weeks, which is addition and scalar multiplication, right? So what we mean when we say that this function, this transformation, should respect addition and scalar multiplication is these equations right here, okay? So for all vectors in V, let's say V1 and V2, if we want to transform their sum, if we want to apply the function to their sum, in order for this function to be linear, it needs to respect that sum. In other words, it should be possible to write it as t of the first vector plus t of the second vector. Okay, so you basically split it apart. And a similar thing for the scalar multiplication. So if I have a scalar k and I want to transform some multiple of the vector v1, I should be able, if this is linear, I should be able to factor that k out in front. Okay, and if I can do both of these things for all vectors and for all scalars, right? If this is true for all vectors and for all scalars, then t is linear, right? It's a linear transformation. Is it making some sense? This is the definition of it. What I'd like to do for the next several minutes is a bunch of examples of this. This is also kind of a reminiscent process to when we were showing that we had a subspace of a vector space. When you're talking about subspaces, remember there's always two parts to it: closure under addition and closure under scalar multiplication. And you had to kind of do a two-part process to check both of those things. Well, this is going to be just like that. Okay, so I've got the first example. I think I actually did write this up last Thursday, but we didn't really have time to get into it very far. But this is an example of a proposed transformation here, t. And I always like to say, what are the inputs and what are the outputs? So the inputs for this particular example will be 2x2 matrices, and the outputs will just be a single real number. Okay, and I've made, but then I have to give you the specific formula where I specifically tell you how do I take an input and then produce an output. So that's what this thing is. This is actually the most important part of it, is the actual formula for the transformation. So I'm going to take a 2x2 matrix, A, B, C, and D, and I'm going to output a single real number, which is just going to be A plus 5D. Okay, so I'm just kind of making that up as an example here. So what I'm going to do is try to show that that is linear. When I say show that it's linear, I just mean that it respects addition and scalar multiplication. Okay, so let's try and do it. You will be doing several of these on the homework for Thursday as well. So this is a good time to practice. Guys, I'm kind of a stickler on the write-up for this, okay? This can't just look like it's all over the place chicken scratch. It has to be very nicely laid out. So please take good notes on this, because you're going to be doing exactly this same thing in the homework for Thursday and next Tuesday on the exam as well. So the first thing I'm going to do is I'm going to show that t respects addition. Okay, so how is that going to work? Well, the t respects addition says I have to take two vectors and add them together inside the transformation. So I'm going to write it as t of, now the vectors in this example for inputs, they are the 2x2 matrices. So I'm going to make a 2x2 matrix A, B, C, D, and I'm going to add that to another 2x2 matrix X, Y, Z, W. The specific choice of letters that you use actually doesn't matter. So if you used A1, A2, A3, A4, and B1, B2, B3, B4, that would not be wrong. Okay, so you don't have to use exactly my letters, but let's try to get this formatted in the way that I'm showing you here. So the first step that I want to do, well, let me ask you what the first step is. If you saw an expression like this, what would you be thinking about doing first? Adding these matrices together or applying the transformation? Which one comes first? Pardon? Adding the vectors together. Why is that? Well, because that's inside the parentheses, right? I have to clean up what's in the parentheses first. So we're not going to do the transformation yet. We're literally just going to add these matrices together. So T of, and then A plus X, B plus Y, and then on the bottom row, C plus Z, and D plus W. Okay, so that is what we would do first. We actually clean up what the input is. See, this formula only knows how to transform a single matrix. So you have to make a single matrix out of what you're given here in order to be able to transform it. Okay. By the way, speaking of formatting this, try not to be falling into that trap of, oh, I'm going to manipulate on the left and on the right. I'm going to be doing random stuff both sides. It's confusing. Try to keep this as just white space. Do not write on the left side anymore. other than just setting it up on the first step. Now what I need everybody to do is make a chain of statements on the right side, and I will be a stickler about equal signs. Okay, this does need to be mathematically written out carefully, and that would include putting equal signs in there. Once I have a single matrix that I am inputting into T, I can now use the formula to evaluate it. How does this formula work? Well, I just have to look at it here. What is the output supposed to be? It says here A plus 5D, but where is that coming from? Well, that's just whatever's in the upper left corner of the matrix plus 5 times whatever's in the lower right corner of the matrix. I'm going to apply that rubric to this input now. So this input, the upper left corner is A plus X. The bottom right corner is D plus W, so that part would be multiplied by 5. So I'm just going to go ahead and write that in into this space right here. Notice that the T has disappeared on this line. The capital T, we're not writing it down anymore. That's because we've already now evaluated T. So we are now looking at the output side of the formula, which is a single real number. Okay, so the 2 by 2 matrices are gone. The T is gone, and I have a single real number here. I'm wondering if anybody has an idea what I'm maybe going to want to do next. You know, sometimes I get stuck in the middle of these calculations. Like, I don't know what I'm supposed to do with that. I just have a little expression here. What you can do is you can cheat a little bit and you can say, where am I trying to get to? What am I trying to end up with? If I look at the right side of this equation, I should end up with T of the first vector plus T of the second vector. Let's just go way down to the bottom and write that down. At the end of this calculation, I want to have T of the matrix A, B, C, D added to T of X, Y, Z, W. Right? That's where I want to end up by the time I'm done with this. Marco?
Separated to A plus 5D and then X plus 5W.
Okay, right. See, when I look at where I'm trying to go to, I see that all of the A, B, C, D stuff should be in the front. And all of the X, Y, Z, W stuff should be at the back. So when I'm looking at this expression and thinking, well, what am I supposed to do with it? Right? A good thought, which is exactly what Marco said, would be to kind of put all of the A, B, C, D stuff first. So I see the A and the 5D right there. I can just put that in the front. And then in the back, I can put everything else, the X and the 5W. Right? So that would be the natural thing to do. Certainly nobody's going to give you any headache about the algebra there. Right? It's pretty clear. I'm just moving the terms around a little bit. But now I see, oh, A plus 5D, that is T of A, B, C, D. And X plus 5W, that is T of X, Y, Z, W. So actually, we have filled in the middle step that we needed, and we're pretty much done. Because we can go straight from here down to here. So, you know, especially when you're first learning how to do these proofs, yeah, you might get stuck in the middle of the calculation. You're like, I'm not sure where I'm supposed to go with it. So don't hesitate to kind of look ahead to what you should end up with by the end of the calculation. That could help you. It's a big clue as to where you're supposed to go with the calculation. Okay, any questions on that? Thomas?
Are there standard formulas that there are for inner products?
There's no real axioms here other than just this set of equations right here. This is basically the whole ballgame.
But like after like for inner products.
Oh, this one?
Yeah.
Oh, no, not really. Well, we do have one standard example of a linear transformation I'll talk about in a little while. But yeah, this could be any formula that somebody might give you. Exactly. Okay, are we done with showing that T is linear? Not yet, because what do we also need to do?
That's scalable.
Check the scalar multiplication part. Exactly. So I also should check that T respects scalar multiplication. Let me set myself up a little space for that one as well. And I'm going to do this in exactly the same way. I'm going to start off with T of some scalar K times the matrix ABCD. So I just put all of that down on the left side. I'm immediately going to block off white space underneath here. I don't want to keep writing underneath there. I'm going to instead go over here on the right and make another column. Okay. Sometimes people get a little bit in a hurry on this one. They say, oh, I'm going to factor the K out. Sure, that's ultimately what you would like to do. You would like the K to be pulled out in front. But if you just pull it right out in the first step, you're kind of bypassing the verification of it. So let's do this slowly. What's the first thing that we would maybe need to do here? Angela? Exactly. Actually do the scalar multiplication, which means the K has to get multiplied into every slot of the matrix. Very good. So this will just become T of Ka, Kb, and then Kc and Kd. We have to make a single matrix that we can now evaluate T. And now the formula for T, we can go ahead and use it because we have a single matrix. And again, it's just upper left corner plus 5 times the lower right corner. So for this input, upper left corner is Ka, and then lower right corner is 5 times Kd. Okay. Again, if you're not sure where to go from here, you can go to the bottom and write down, what you're supposed to end up with. But I bet somebody might have an idea for me here. Would you have a suggestion looking at this expression? What might be something easy that we could do? Blake.
Factor out the K.
Factor out the K, exactly. Go ahead and pull out the K, factor out the K, and that leaves me with A plus 5D. And now I've got the K on the outside and the part in the parentheses. Well, that is just T of A, B, C, D again. So I should be probably putting little check marks on these verifications because this is really what it is. We're doing a little proof here. Okay, so T is linear. Okay, this is a good example of a linear transformation. Make some sense? Okay, you might wonder who cares why T is linear, or who cares if a transformation is linear, but I am gonna come back and talk about that in a little bit. I first would like to do a few more examples. Let's do another example. For number 2, I'm gonna define T. This time I'm gonna go ahead and work with an n by n matrix. Again, I will spit out a real number. And my formula this time is going to be T of capital A is going to be the determinant of A. So this is a natural way to take a square matrix and spit out a number from it. Okay, and this time I'm going to ask it as a question: is T linear? Just meaning, is T going to respect addition and scalar multiplications? It's kind of a yes or no. And so this time, instead of proof, I'll just say solution here. I should point out a little bit of a difference between the two examples. You might notice on the first example, the input was totally expressed using all of the entries of the matrix. You see the little a, the little b, the little c, the little d, and that's because the formula that was given to us really was hinging on the entries within the matrix. So you see that I've got it all spelled out here. Whereas on this example, everything is much more surface level. I'm just calling my matrix capital A. I'm not getting into the nitty gritty of, well, what are the entries of A? I'm just writing it very boldly as an abstract letter, capital A. And that's because the formula that has been proposed here is totally expressible just in terms of capital A. I don't have to get in the weeds with what are all of the rows and columns or any of that. I can just express it as a single cleaned up expression, which is the determinant of A. So because of that, then of course, if I start trying to write things up, right? So if I start looking at T respects addition, right? I can start off with, just T of, let's just use capital A plus B here. So we can take our vectors like so. And, just like the first example, the first step is to add the matrices together. And that's what I did here. I added the two matrices together. But the difference here is, since it's being done on a surface level, and it's so abstract, we really can't simplify that any further. Like, how could you write this any more, succinct than this? This is really what it is. So the two matrices have already been added together. This is as cleaned up as it gets. We don't have to actually, like here, we were combining the different slots together to get a simplified matrix. This is already simplified, which means I'm already able to just go ahead and apply the transformation to this input. And so the formula would be determinant of A plus B. Right? And again, you might get to a place where you're like, I don't know what I can do with that. Remember, it's always okay to go to the bottom and say, well, let's think about T of A plus T of B. That would ultimately be where we would be heading with this, right? And so the question is, can we get from here to here? I see people shaking their head no, which I'm happy to see that. I mean, we could try to work backwards. By the way, working backwards is fine. Just make sure that you're organized. You still have the white space over here, right? We don't want to put anything on that side. We're just messing around on the right-hand side. So if we worked backwards for a moment, we could say, well, to get T of A plus T of B, we would have to have determinant of A plus determinant of B. So now here is my question. Is this legal? To go from this line to this line? It's not. It's actually not legal because, back when we were studying determinants, we had all these properties of determinants, but I will remind you that I had a warning for you back then that determinants are great for transposes, for inverses, for multiplication, but there was no formula for addition, right? There's no nice formula for addition. So this fails. Now, when something fails, you probably remember for these last few weeks that generally what we would want to do is give a specific example to show that it fails. And we can do that here very easily. So this fails. Go ahead and indicate that here. We tried to make it work, but our intuition is that it's not going to work. So what we would do then is hopefully give a specific example. So we could come up with, two specific matrices A and B. I'll probably just make them both 2 by 2. Let's just make n the smallest value of n for which this is kind of worth thinking about would be a 2 by 2 matrix. And we could come up with many examples. Let's see. Eduardo, what's your favorite 2 by 2 matrix?
The identity matrix.
Okay, 1, 0, 0, 1. Sounds good. Adon, what's your favorite matrix?
1, 1, 0.
1, 1, 0, 0. Okay, let's check this out. So the determinant of A, what is the determinant of the identity matrix? 1. Okay. What about the determinant of the matrix B here? 1, 1, 0, 0. That'd be 0, right? You can use the little AD minus BC formula if you want to. So now let's add them together. So A plus B. So we add these together slot by slot. There's a 2, a 1, a 0, and a 1. And we can say, well, what is the determinant of A plus B? What would be the determinant of this little matrix here? 2. It's 2, right? Okay. And so you can see right away that that is not this one plus this one, right? So this shows that T of A plus B would have been 2. But T of A plus T of B would be 1 plus 0, which is 1. So they don't agree. They don't agree. So T does not respect addition. Does not respect addition. Okay. Do we need to explore the scalar multiplication then?
No.
Right? Just like all of our previous experiences, right? If there was an axiom of an inner product that failed, it was game over. If there was a axiom of a vector space that failed, it was game over. We don't have to drag ourselves through the whole list of properties. If any one thing fails, then the answer is no. Right? We don't actually have to check the scalar multiplication at all because the first axiom has already failed us. Yeah, so that's a good thing to always keep in mind. Are there questions on that example? So this one is not linear. The determinant is very nice for lots of things, but not for being linear. That's one thing that we have to wrap our heads around. You guys might remember when we were doing subspaces, for a set to be a subspace of a vector space, of course, it has to be closed under addition and closed under scalar multiplication. But you guys might remember that there was something that we would generally do first before we dive into checking the addition and the scalar multiplication for a subspace. Do you remember what that was? That was kind of a quick thing that we could do right away, Johnson? The zero vector check. You guys remember that? If that zero vector check failed right off the bat, well, then you could just stop already. It's game over already. You say, nope, it's not going to be linear. Or sorry, it's not going to be a subspace. It's not going to be a subspace. So you might be wondering, is there something like that here? Is there something we could do quickly so we're not just diving into these longer verifications? It turns out that there is. Okay, so I'm just going to make a quick remark here, and then I'll show you a quick example of it. There is a zero vector check for linear transformations that I'd like to share with you guys. And here is what it is. Here is what it says. It basically says that if t from v to w is linear, if it's going to be linear, then that transformation, so if t is linear, that transformation must send the zero vector of v. So I'm going to denote that with a sub v here. So this is just whichever is the zero vector of the input vector space. That has to be equal to the zero vector of the w space. So this is the sort of analog of the zero vector check for linear transformations. If t is linear, then it has to pass this zero vector check. And if that check fails, you can stop right away. Let's be careful though, because this zero vector check does not work in reverse, right? Just like if the, you remember, if the zero vector was a part of your subset, that didn't guarantee that you had a subspace of V, right? It just means the zero vector check passes, and then you have to still analyze whether it is closed under addition and scalar multiplication. Same thing here, guys. Just because the zero vector check passes does not mean that t is linear, and we have the perfect example right here. If you take a look at this, right? So in our example, so in example 2, it is true that if we take t of the zero vector, which in the world of n by n matrices would just be a matrix of all zeros, it is true that that is equal to 0. The determinant of the all zero matrix would be 0. So you can see that the zero vector check in this example passes. It passes the zero vector check for linear transformations, but t is still not linear, as we just saw a moment ago. Okay, so however, t is not linear. So just as I warned you about the zero vector check in chapter 4 for subspaces, I have to give you another warning here, which is that don't read too much into this box. Okay, just because t of 0 equals 0, that does not guarantee that t is linear, and we need to look no further than this example to see how that could maybe break down. Okay, but the way that you really want to use this remark is when it fails. Because if it fails, oh my gosh, you can just stop right away. Let me give you another example. So let's continue with our examples here this morning. Just want to kind of give you a lot of practice with this idea. Okay, so let's do this one. Number 3, let's define T. This time I'm going to go from P2 of R as the input, and I'm going to map it over here to the output, which is M2 of R, via. I'm going to make another example for us to look at. And in this example, I'm going to take T of, let's just plug in a polynomial, ax squared plus bx plus c. So it's a quadratic polynomial. That's what my input vector space consists of. It should look like these kinds of polynomials here. And then I have to output a 2 by 2 matrix this time. Okay, so this time the matrix is on the output side, and here's the output I'm going to use. The first row is 0 and -1. The second row is 2a, and then b minus c. So let's go ahead and make this example. And I'm going to ask it also as a question, is T linear? This is what we were going to think about for a moment. And I could, start checking whether T respects addition and scalar multiplication. But actually, before we do that, okay, just like I did in chapter 4, I'm going to recommend that we do this 0 vector check first. Okay, so let's just do the 0 vector check. So sorry, this is the solution now. I'm actually going to do the 0 vector check because it's easy. It's fast and it's easy. And if it fails, then we can stop very quickly. It's a game over immediately. So for the 0 vector check, I'm going to plug in the 0 vector here. Now, do people know what that means, the 0 vector for this polynomial world? Johnson?
Are you gonna put 0 in place of ABC?
Exactly right. In case you didn't catch that, we are going to put the zeros for the A's, B's, and C's. Sometimes I see people trying to plug in 0 for X. That's actually not what we want. We actually want to imagine what is the 0 vector in the world of polynomials. In the world of polynomials, the 0 vector is the one where every scalar is 0. So A is 0, B is 0, and C is 0. So if I use that as my input, then it makes sense over here to just fill in A, B, and C all with 0. And so if you do that everywhere that you have A's, B's, and C's, you should just get this matrix right here. And my question is now, is this the 0? Have we gotten the 0 vector from W out right here? Not at all, right? This is not the 0 vector for W is, of course, this vector space here, right? V is always the inputs, W is always the outputs. So you see that, yeah, this fails. This fails right away. So if it fails, the 0 vector check, then the answer is immediately no. We don't even have to go any further with thinking about this example. It's automatically not going to be linear. Okay, so this 0 vector check is worth doing. It doesn't take very long. It's usually very easy, and if it fails, you can get a quick answer to a problem. Okay, let's try another one. Okay, more examples sounds good. All right, let's do a few more examples. So let's do number 4. So on this one, I'm going to define T. T is this time is going to go from R2. So inputs is going to be R2. And the outputs is going to be P2 of R. And I'm going to give you the formula here that we're going to work with. The formula, I'm going to take T of, so I take 2 inputs, A and B, right? The R2 would look like A comma B. And I'm going to spit out a quadratic polynomial, right? So here it is. I'm going to spit out A plus the quantity B minus 2A x squared. We're going to use that formula, and then we're going to ask, again, is T linear? Same question again. So for the 4th time already now, we're going to give this one a try. What would you suggest I do first? If anything I've been saying the last 5 minutes is helpful, I would recommend we do the zero vector check, okay? So let's start with that zero vector check because it's fast, it's easy. So for the zero vector check, let's see, how does that work again? I'm just going to check this out. If I take t of the zero vector, do I get the zero vector? So let's try it. Let's put in 0. So you have to know that the zero vector of R2 is just the point 0, 0. So I'm going to plug in 0, 0. That just means everywhere I see an A or a B, I'm going to replace it now with 0. So what is this going to be? Well, it's 0 plus 0 minus 0. Well, sorry, 0 minus 2 times 0, x squared. And if you just look at that for 2 seconds, you'll realize that that is actually 0. So it passes this zero vector check. Okay, so in a sense, this was a waste because since it passes, we still have to go on, but it was not much effort, right? And if it had failed, we would have already been done. So I think it's worth it. Okay, so since it passes the zero vector check, now I'm going to start thinking about whether t will respect the vector space operations. So I'll maybe put that over here. So let's look at the addition. I usually just go in order. It doesn't matter, of course. If you wanted to do the scalar multiplication first, you could, but I'm going to do the addition. So how does that work? So I have to do t of 2 vectors added together. So I'm just going to maybe use the vector AB that we already have, and I'm going to add another vector, which maybe I'll use the components of C and D. Okay, I'll kind of set it up like that. And again, I'm going to do nothing but white space down here. I don't want to be writing anything on the left side at this point. I'm going to focus on the right side of this column. What's the first thing that you would have me do here? Blake.
It's TA plus B, plus T, wait, TA plus C plus TB plus D.
Well, there's only one t, so I'm going to say I'll put the t on the outside, and then I think you're getting the right stuff on the inside. I need to add the, let's just write it down, it'll look more obvious. I'm just going to add the slots together. So the first slot is A plus C, and the second slot is B plus D. Again, guys, if you didn't like that, you could have used X and Y here, or you could use S and T, like any letters you want. There's no right or wrong choice for that. But in this case, I just chose A, B, C, and D. Okay, I have now created a single input that I'm gonna, this is the all important formula, okay? So let's read how this formula is supposed to work. When I plug something into T here, I have a constant term, which is just whatever the first slot was. So look over here, what's the first slot? That's A plus C, okay? And then I have an x squared term, and what's the coefficient in front of it? It's the second slot minus 2 times the first slot, right? So if I look at the A and the B here, where are they showing up in this coefficient? Well, we have B minus 2A, second slot minus 2 times the first slot. So I'm going to use that to help me figure out what goes right here. Second slot is B plus D minus 2 times the first slot, which is A plus C. All of that is times x squared. So parentheses are kind of your friend here, kind of help keep this from getting too confusing. You might want to use like I did here, some somewhat bigger brackets. This is an important step. I am essentially just plugging in A plus C everywhere I see an A here. And I'm plugging B plus D everywhere I see a B here in the formula. Is that looking okay? All right, super. Any thoughts what I would want to do with that now? Angela?
You could put them into their own kind of respective equations that mimic the format of that.
We want to mimic this formula, right? We would like to get kind of reorganize these terms, right, in a way that is more lined up with how this is supposed to look. Again, if you're not quite sure what to do next, you can always go to the bottom. Don't forget, on the bottom, you're going to have T of AB plus T of CD. And the question is, and it is a question, is it linear? The question is, can I work my way down to this, okay? And what you see is that all of the A and B parts should be in the front, and all of the C and D parts should be at the back. So the strategy should be to try to reorganize these terms. So I see the A here, keep it in front. Anything that has an A or a B in it, I'm gonna put it up in the front, and you can see right away that it's exactly in the brackets here, B minus 2A is the A and B part that gets multiplied by x squared. So that's all kind of together, the A and B terms, and then I'm gonna add to that all of the C and D terms on the back end. So I see a C right here out in front by itself. And then in the brackets, I still have to account for the D minus 2C. And that's times x squared. Just enough room to squeeze that in. But that's what you'd expect to end up with. And then when you look at it, oh, the first part, that's T of AB, according to the formula. And the second part would be T of CD. If I just, instead of A and B, I had C and D, this is what it would give me. So you're done with this part. Check there, right? That's verifying that T respects addition. Okay. Is that too fast? Is everybody okay with that? It's a little bit of algebra is all, Derek. I mean, it's basically just, there's a lot of alphabet soup of letters here. The A, B, C, and D. I really do think that it's not a bad idea if you're kind of getting lost in all of the expressions that you see here, to go to the bottom, write this down, because this is ultimately what you're supposed to end up with, right? And then you can just go from here back to here. Right? This is not such a difficult step, right? To just say, okay, T of AB would be that, T of CD would be that. And then you just have to look at these and say, are they the same? Do they algebraically match up, right? You could hand this to somebody who's in pre-cal and just ask him, is that the same as that? See if they can do it. Give them a little homework problem. Anyway, so that is all that it is at that point. It's just the algebra of it. Oh, sorry, I'm not done, am I? I was going to use this space right here. I have to also check that T respects scalar multiplication. I think I'll just do that right here. And let's see if this one works out. T respects scalar multiplication. Let's give it a try. So if I wanted to do that, I might look at T of, okay, so guys, I'm looking at the second axiom. There should be a K now. So I'll have K times AB. So K times A comma B. And what should I do first here? Put that K on the inside of it. So guys, don't be too hasty to pull the K out in front. Before we can get it out in front, we kind of counterintuitively have to embed it inside a little bit better first. So it just becomes T of KA, KB. And now everywhere I see an A, I'm now going to put KA, and everywhere I see a B, I'm going to put KB in this formula. So let's do it. So the A is now going to be KA, and then in the parentheses, the B becomes KB minus 2KA. And all of that is times x squared. Okay. So that's just applying the formula in the box, but modified with, KA playing the role of A and KB starring in the role of B, that kind of thing. So that's essentially what it is. And what would you suggest I do with this thing?
Okay.
Now I can factor the K out of everywhere, right? And if you want to, you can just do that in one step. So I'll factor the K out. I get A plus, and then the quantity B minus 2AX squared, which is all in the brackets like so. And then the last step is to make sure that it's really looking like what our definitions over here require, which is that we should be able to rewrite this as K times T of A comma B. So that also gets a check. So this one passes everything. It passes on everything. So this is a yes again. This one will be a linear transformation. Okay. Let me see how I'm coming along here. Everybody kind of with me? let's do another example. This next one is super important. So all of the examples that we have done so far, it's really just been one specific problem that I have created kind of out of thin air. I've just kind of created, oh, here's V, here's W, here's my formula. What I'm gonna do in this next example, guys, is I'm actually gonna be actually doing a whole family of examples in one breath, in one example. So you'll see what I mean. This is gonna be a big deal, and there's a lot of homework on this as well that we'll look at on Thursday, this next example. So you're gonna wanna perk up a little bit for this. And then I think that'll help you out a lot with the homework. So number 5 is, like I said, it's not one specific example, it's a whole general family of examples. And the way it works is you're going to start by fixing a matrix, capital A, and the size of that matrix, I'm just going to call it M by N. M rows and N columns. The thing that's a little bit ironic about this is that my V and my W that I'm about to tell you has nothing to do with matrices. Somehow the matrix is going to be here. So what I'm going to do, guys, is I'm actually going to define my transformation T to go from Rn to Rm. So the vector spaces, the V and the W, are actually not like matrices. They are Rn and Rm. And by the way, please check the M and the N. They do get flipped. And if you don't flip them, it's not going to work. So if this is an M by N matrix, then the transformation will go from Rn to Rm. I'm pretty sure there's a true false item on that for Thursday where they've got them switched to see if you notice that. So you have to switch the order of these. And now defined via. So now I'm going to explain how you do the transformation. And here it is. We're going to plug in a vector from Rn. I'm going to call it X. And the output needs to be a vector in Rm, right? And the way I'm going to actually make that happen is I'm going to take this fixed matrix that I had ahead of time, and I'm going to multiply it by X. Okay, guys, you can think of this X as an n tuple. I actually want you to think of it as a column, not as a row. So think of it as an n by 1 column that you're inputting into this transformation. The matrix A is M by N, and the vector X is N by 1. What size matrix do you get if you take an M by N matrix and multiply it by an N by 1 column? What size result do you end up getting? M by 1, right? Well, that's perfect because I'm supposed to get an output that has M slots in it. Okay. This type of formula, right? When I said that this isn't just one example, it's an entire family of examples. What I meant by that is that you can change this matrix A all day long. 5,000 times, that will give you 5,000 different linear transformations. It doesn't actually matter what capital A is. This will always be linear. Okay, so this is always linear. We don't even have to worry about it. I am going to show you that it's linear really quickly here. So I'm just going to check that. I'm going to check that T respects addition. I'm going to just show you the details one time. Oh, the beauty of this is I only have to do it one time, right? October 22nd, 2024, Dr. Annan is verifying that any transformation of this form will always be linear. That means from now on, forevermore into the future, you don't have to check it again, right? You can just quote this fact, right? So let's do it. So T of, let's say X plus Y maybe. I'm gonna add to, as by the way, I'm skipping the zero vector check. It will pass that for sure. So I'm gonna ignore that and just go straight into the addition here. The way the transformation works, according to the formula there, I just take A times whatever I plugged into the transformation. So it would be A times the quantity of X plus Y. And what do you suppose I'm gonna do on the next line there? AX plus AY, right? That's the only thing I could think of to do. A times X plus A times Y. Okay, and that is nothing more than T of X plus T of Y. So that's the verification on the addition part of it. And then I'm gonna check that T respects scalar multiplication. I'll do that right here. I don't need a lot of room for this. This is pretty short. So I just have to take T of, well, it would be K times X. So I take my scalar K this time. And again, it's so abstract, it's already simplified. So I don't have to do anything other than go straight to the formula. The formula tells me just take the matrix times whatever that vector was, which is Kx. And what do you suppose that I'm going to do with that? Put the K out in front. Be a little careful. I mean, if you're a little nervous about that, that would be reasonable because we do know that normally matrix multiplication does not commute. If this was two matrices side by side and you were trying to switch the order of them, I would probably object to that. Because normally you cannot do that. But this K is not a matrix. This K is just a number, and so it's perfectly reasonable to pull it out into the front. And so that's what I'm doing right here. By the way, I still have my white space on this side, not writing anything on the left side. Well, technically it's right here. Right. So I don't write anything down there, but now here I just have K times T of X. And that checks that T respects scalar multiplication. Awesome. So that verifies that this transformation in the box there on that middle board is linear. It is a linear transformation. Okay. And this is kind of like in chapter 4 when we proved that a null space is always a subspace. We don't have to keep checking that every single time we have a new problem, right? If we see that a set was created that was the null space of a matrix, we can just say, oh, null spaces are always subspaces. Therefore, we don't have to go any further, right? Same thing here. This kind of linear transformation is always linear. We don't have to keep harping on it. We don't have to verify it again, right? We are all witnesses right now to the fact that this kind of formula will respect the vector space operations. Okay, there's a name for this kind of transformation. Any T from Rn to Rm, as in whatever it is, example 5 above, is called a matrix transformation. This is always called a matrix transformation. All right. So what we have basically verified here in the middle board is that a matrix transformation is always linear, right? So just as a conclusion, matrix transformations are always linear. You can quote that. You can just say that. If you see a problem where it's relevant and you want to just state that, you go right ahead and do that. You don't have to stop and check that T respects addition and scalar multiplication. Why not? Because I already did it right here. once and for all. Let me give you an example of where this might come up. Right, so as an example, maybe we can call this 5A. It's still kind of part of example 5, but I'll just call it 5A. But what if I asked you to show that T, I'm gonna make T go from R3 to R2. By the way, one tip that you're maybe dealing with a matrix transformation is if you see Rn and Rm, right? So be careful with that. If it's not R something and R something, then we're not in this matrix transformation discussion. So if you have a problem that has polynomials in it, or calculus functions, or even if you have like matrices right here, right? That's not the form of the matrix transformation. The matrix transformation goes from Rn to Rm. The matrix is actually the vehicle that does the transformation for you in this situation. The matrix itself is not the vector, right? Is everybody following this? The matrix is not the vector. Johnson?
Or M and always in different numbers.
No, they could be the same. Yeah, the M and the N don't have to be different. But in this example, I'm going to make them a little bit different. But here we go. So let's continue this example. Defined by, so I'm going to take T of, I guess this time I'm going to use XYZ. So I'll plug in XYZ, and then I have to spit out 2 slots. Let's spit out 3x minus z, and then also negative x plus 2y plus 4z. So I'm going to show that transformation, is everybody with me? I plugged in 3 numbers, and I'm spitting out 2 numbers, 2 slots. Show that is linear. The idea here is show that is linear. So, of course, we could do it the way I've been doing all the earlier examples. I could do T of XYZ plus ABC, and then I could like do this whole big messy calculation. Or I can do it the easy way, which is that I can try to convince you that this is just a matrix transformation. Because it is. It's just a matrix transformation, as it turns out. So, so for the solution, let me show you what you could write down for this. Right, what I could do here, guys, is I could actually write T of XYZ as something involving this matrix. By the way, what size matrix do you think would be involved with this transformation? Right, don't forget that the M and the N, right? So N is 3 and M is 2. So the size of that matrix would be a 2 by 3. But do you kind of see how these expressions they look like dot products to me? Something X, something Y, something Z with numbers in front of them. Couldn't I just kind of put my XYZ right here as a column? That's like my input vector. And then just get the correct scalars. So 3 should be multiplying by X. There's no Y, and there's a -1 on the Z term in this first slot, right? I'm just looking at the first slot. So if I do this dot product, I will get 3x minus Z. You see? And the second row would line up with the second entry of this given function, and I would need to have what numbers on the second row? -1, 2, and 4, exactly. So this is just the same exact transformation as this one is. It's just written a little bit differently now, where we're actually pulling out the matrix. This thing right here, this is your capital A. That is your matrix capital A. And so what you can do is you can just say T is a matrix transformation. I probably would want you to say more than just that. Of course, we know that matrix transformations are always linear, so you would be able to be done already. But I would actually like you to tell me what the matrix is. So, so I would want you to write down what the capital A is for your particular problem. and here it is. And that would be your solution. That would be the entire thing. That would be the entire thing. That seem okay? What would you rather do? Would you rather do the t respecting addition and scalar multiplication? You know, got x, y, z, a, b, c, add them all together, do a bunch of algebra here, and then do the scalar multiplication as well. Would you rather do that? Or would you rather do this? I hope you're gonna say this one. You gotta get that right. Yeah, this is so much faster and easier. Okay. So if I give you a linear transformation that goes from Rn to Rm, we can write down the corresponding matrix very easily. You notice the numbers in this matrix, you literally can just read them off from here. You don't even have to hardly show any work. And you can just make sure you've got the dimensions correct. It should be a 2x3 matrix, and these coefficients just get thrown into the matrix. So there's at least 2 or 3 homework problems for Thursday that are just this, and they should take you like very little time, as long as you're taking advantage of the fact that these linear transformations, matrix transformations are always linear. So that's one thing. And by the way, you can go in reverse as well. Let me say one more quick word about this, and we'll take a little break. In this example, I started with the linear transformation and I plucked out the matrix from it. I figured out, well, what is the matrix that is the vehicle of that linear transformation? You can also reverse this process, and I could start with a matrix and ask you to create a linear transformation from Rn to Rm out of that matrix. So let's just do one more example. I'll call this one 5b. This is basically just turning the previous example around. This is also not very difficult. So let's just say I give you a matrix. So better marker here. Let's let capital A be the matrix. Well, let's just do this. 1, 2, and then 3, 4, and then 5, 6, and then 7, 8. And then let's just say I ask you to write a formula for the matrix transformation So I'm going to try to write the formula for the matrix transformation. T of x equals A times x. Okay, so I definitely want you to be comparing example 5a with 5b. On 5a, I started with the formula and then wrote down the matrix. Here, I'm just turning it around. I'm starting you off with a matrix. And I'm going to ask you to write down the formula. So my first question for you is that this is a transformation from what to what? Louder?
It's R2 to R4.
R2 to R4. Excellent. Exactly right. We figure that out by just looking at the size of the matrix, yeah? This is a 4 by 2 matrix, 4 rows and 2 columns. So the M is 4 and the N is 2. And so this would be the inputs and output. Now, this is not the whole formula. Sometimes people just write this down and think that's the whole thing. This is just telling me what are the two universes that are involved in this transformation. But I actually want to write the formula. So that means I need to tell you what is, T of two things that I plug in here. I'll call them X and Y because this is coming from R2. Now to help us get this right, we do want to remember that, okay, the output should have 4 slots, right? It's coming from R4. Now, how does this transformation work then? Well, I'm just going to take the matrix and multiply it by the vector. Do note that I'm going to be writing the vector as a column. I know right here, like you might wonder, well, why didn't he write it like this? shouldn't it be like a 2x1 input? Technically, yeah, it would make sense to draw it like this. If you wrote that, I would know what you meant. But usually people want to save paper and space and stuff like that. You start drawing lots of vertical columns, it just takes a lot of room. So that's why it's more typical to just see it written this way. But you have to kind of understand that really what's going on is that this XY is going to be a column over here. So I'll draw it as a column when I actually write out the matrix multiplication. So let's just come back here, guys, and we can put in the numbers now. To figure this out, all I really have to do is do the matrix multiplication. Okay, so the top slot would be x plus 2y. And then the second row, we would have 3x plus 4y. The third row, we would have 5x plus 6y. And the fourth row, we would have 7x plus 8y. Exactly. And then probably I would be okay if you wrote the answer that way. But if you wanted to, especially if you're trying to line it up with the back of the book, it would be, again, customary to just rewrite that as a row expression. Takes up less vertical space in a back of a book answer, for example, to write it as a row. So you might write x plus 2y, 3x plus 4y, comma, 5x plus 6y, comma, 7x plus 8y. Right. Does that make a little bit of sense? So there you go. Make sure that everything is on the up and up. We should have 2 inputs and 4 outputs, right? R2 to R4. So if those are not, if you're not coming up with the correct number of slots, that's kind of a red flag that maybe I need to go a little more carefully and double check something. But that's basically it. Given a matrix, you can write down this transformation. You don't have to stop and check if this is linear. You know it's linear because it says it's always linear. And that's because Dr. Annan has checked it now once and for all. Forevermore, we know that this kind of transformation is always linear. Yeah, so you guys were all present and accounted for. Anybody who's absent today will have to verify that it respects addition and scalar multiplication every time because they didn't see it. Just kidding. Anyway, one last comment before we take a short break. I'm sorry, I meant to say this earlier. You notice, let's go back to the example 5a. We're inputting a formula and outputting this matrix. I just wanted to point out that you can actually see these columns in a slightly different way. If you actually, so sorry, if we could go back for just a second. This is my bad, I got too excited. If we actually were to plug in the standard basis vectors on R3, so like if you plug in 1, 0, 0 for X, Y, and Z, let's go back to this example, take a look, what would you get for the output here? Anybody awake out there this morning? Plug in 1 for X, 0 for Y, and 0 for Z into this formula. What do you get? 3 and -1. Thank you. 3 and -1. What I was going to try to point out is that that happens to actually be exactly the first column of the matrix. Okay. And then what is T of 0, 1, 0? If I plug in 1 for Y everywhere, I don't have any Y in the first slot, but I have 2 Ys in the second slot. So it's 0 and 2, which is, of course, exactly the second column of the matrix. And finally, if I do T of 0, 0, 1, you can see that if I put in a 1 for Z everywhere, I'll get -1 and 4, and that is exactly the third column. And that is actually a general fact. That for these matrix transformations, I'm going to write it here in the notes for you guys. In general, so now we can make a quick comment here. In general, the matrix capital A, which is M by N, for a matrix transformation is here's how you basically can get the matrix. you simply fill out the columns to be the transformed standard basis vectors. So you can take T of, I'll call it E1. Do you guys remember when I used, when we were talking about standard basis for a Rn? The standard basis vectors are just E1, E2, E3. It's just these vectors here, right? This 1, 0, 0, this is E1. 0, 1, 0 is E2. 0, 0, 1 is E3. Those are just the standard basis vectors on Rn. And so what I'm hoping that you guys are picking up on here is that the way this matrix is created is that you simply are transforming all of the standard basis vectors and laying the results into the columns. And that's how capital A is created. You notice it has n columns, which is what we would expect. And it will also have m rows. It's an m by n matrix. Yeah, okay. This really goes with 5A more than anything else. I just kind of overlooked that. But you're gonna want this fact on some of the homework. So it's just nice to know that. All right, I think I'm feeling pretty good about this stuff. There's still the question of who cares if T is linear, what's that good for? But I think I'm gonna wait till we take a little break first. So why don't we take a 10-minute break? I've got some problems on that side board over there that I'm gonna do when we come back from the break from tonight's homework. So we'll do that, and then I might say a few more words about why we care about this stuff as well. But we're pretty well done with this section. So I'll see you guys at about 11:20. That clock is wrong on the wall. 10 minutes from now, we'll pick back up again.
I think that's exactly why they're trying to, not. Going to the one that's really hard. I have seen lessons, because when I first moved in, I saw like, okay. Just like, it's this problem where you live with it. Well, that's what I'm saying. And then, interconnection.
But no, you shouldn't even have a view.
Huh?
You shouldn't even have a view.
It's an old house.
I've
It really depends on what you think.
It just means that place in the front. I don't think it has anything to do with big healing.
No, it's definitely HS something to do with it. Because like, for example, like my office where I went, we're in the little portables, so we get answers. Because it's an old building that wasn't meant to be used this long. So it's way easier for them to get in.
The gas can get in anywhere thing.
Yeah, they can, but if there's two houses, one has, and they both have food, they're gonna get the one that's easier to get into.
I thought ants come as a placement.
Use a lot?
Like just where they're placed.
Yeah,
Where's the ant
basically.
hill and that's it.
Yeah.
Like I don't think it matters. I mean food matters, but I don't think it matters for the lizard.
I'm just saying it makes it.
Yeah. They probably have that problem like every year.
Yeah.
We should get ant traps.
It's
It's like $3. Yeah.
over
Target.
I'm so glad to about this. I need to add
Called ant bait. Yes. You would?
like droppable.
Dude, my
So
parents got stuff that like my grades aren't supposed to. Like their past, their stories.
No.
One time I was talking to my mom, she like just casually dropped that she was a widow at 18, and I was like, oh, you can't just casually tell me that. Like, what the heck?
You didn't know that she, wait, what if somebody was married and then husband? And she didn't tell you she had previously.
Well, she did. She didn't tell me. He died when she was 18.
Oh, do you guys want to know something?
Oh, but you
funny
knew
about
he
my
died.
grandson?
Well, not even to be honest.
Really?
What?
You thought he was still alive?
Well, I knew he wasn't. I don't know. I don't know.
Yeah, because that is like a big thing to like tell somebody.
It was like a million decades ago. My mom was 18 a long, long time.
I know, but I feel like I would want to too.
Well, after that, I did. I was like, you have to start.
Yeah, like I should know everything that is.
First, I'm like, when about 18? When did you get married? And then I found out she got married at 15, and I was like, whoa, whoa. The 70s were different. Well, that was really even back then. But like,
15 is really.
1975, she was married. 1978, she was a widow. Isn't that crazy? It's like, damn, you experienced more life than me at my age. At 18, I was still like in high school trying to figure out what I wanted to do with my life.
Dude, I was like adult when I was. No, maybe not.
I was. I keep.
I keep it. Okay. I was playing Minecraft when little get like that.
She did it to me again this morning. Okay, so she asked me for money a lot. And even though I don't make a lot, I still get money back. It's just sounds like, but it's still needs money. Basically, we have a relationship where I give her money and then remember to give her money. And it's just like a cycle like that.
Yeah.
Rambling. She asked me for money this morning for propane. I said sure. And then she was like, oh, thank you. I don't know what I do with that. And I was like, oh, you were doing it. I was really where I went to go around you. And she was like, sometimes. I was like, sometimes. And then she was like, I had to do things I wouldn't normally do. And I was like, and then she was like, love you, have a good day. And I was like, you can't just say that. I don't know. Oh, I love that. Well, sure.
So my mom's parents were both married together. They swapped. Like my grandfather and his ex-wife divorced, and then their exes got together and they
so wait,
I'm so confused.
she got drop family tree.
Yeah, it's like when you see my sister's cousin's brothers. You know what I mean? You're like this.
Okay, which one's your grandparents then? It does matter. It does.
Because we need.
It is. Maybe.
Okay, so they got together after. I was wondering if they got together before. No, they had divorced grandparents. So that means if they didn't swap, you wouldn't. Yeah. That's great. They didn't like swap. Because they have to.
I think it's easier for you to just say both of his parents
had kids.
But to each other, they're technically step siblings. Yeah, his parents are siblings. Wait, I gotta draw the kids.
So his parents just don't
You could have kids. Yeah, basically.
thought your partner.
They decide to. Well, I'm not Yoshi, but that's not part of the story. I mean,
I don't know if I'm following this correctly. 'Cause
Okay,
it's
look,
like if
look.
my parents got divorced, had partners, and then had kids, isn't that what you're just?
Okay, we're doing lots of stuff. It's normal that he has half siblings. I just thought it was funny how his half siblings are half siblings. That's different.
Oh.
Oh my god, I can't. I don't know. what you're
Look,
talking
I
about.
added pink and black.
Oh, his.
Dry house.
See, look, he's related to them. She's the last. They're not related to each other. They're stepstones.
I think I'm just gonna.
You understand?
I'm like partially. I'm stuck there.
All 1,000 followers are gonna hear my family. Well, they know who you
Oh, no, it was just, I got. It was fun.
I like the hat.
Thank you. Yeah, I almost never wear them, but I got I was telling, I got sunburned 2 days ago and I'm trying to like keep myself. What's that? Oh, right, I never wear these things, just because I just trying to get no more light on it right now. So it might be for the whole week, I have to kind of keep it protected. I didn't think I would get sunburned in October. It's the middle of summer, but at that altitude, it's actually pretty bad. Anyway,
Oh, I thought you were from basketball.
well, that was also not good. Yeah, I did play yesterday and, yeah, it was a lot of sun. So. Yeah, guys, I don't think any of you came to the basketball yesterday, but I'll probably do it again. My team won every game, just so you know. We did really good. It was a good time. We had about 8 people showed up, so it was fun. One of these, probably not next Monday, because we have a test on Tuesday. That might not be such a good day, but one of these days I'll set up a rematch. See. Play basketball, let's do midnight. Number 211. We did. We spent a lot of time shooting. It's fun. Had a good time. It was a good workout. Yesterday was hot, man, outside. Okay, guys, why don't we go ahead and gather back up here for a few more minutes. I'm gonna try to talk for only 10 more minutes about this section. There's just one last thing I want to do, and then we're gonna probably spend the rest of today helping you with tonight's homework. On Thursday, well, that if I am successful with all that, I won't have any new material to do on Thursday. So Thursday will be just 2 group works and going over Thursday's homework and kind of just getting ready for the exam. I think that would be awesome. So, but let's take a few minutes and I want to say one more point about this, which is getting a little bit at the heart of the question, why do we care if T is linear? So linear just means again that T respects addition and scalar multiplication. Thereafter, we also made the comment that T will respect the 0 vector. That was the 0 vector check. We talked about that a little bit ago. And I want to add one more thing to the list now, and this one should not be a big surprise. I'll just call this a remark if I can for the notes here, which is that if T is linear, so if T is linear, then not only does T respect addition and scalar multiplication and the 0 vector, but then T will actually respect, so T respects actually all linear combinations. Right? And I'll put a little colon here. I'll write this out in just a second. But if T is going to respect addition, and if it respects scalar multiplication, then kind of putting that together, putting those two things together, what you can say then is that if you ever had like T of C1 times V1 plus C2 times V2 and dot, 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 up to Cn times Vn, if you had some expression like that, then in that case, T has to respect the entire linear combination. In other words, you can totally bust it apart. So I can write this as C1 times T of V1. And C2 times T of V2 and plus dot 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 plus Cn times T of Vn. So what you're doing here is you're pulling out all the scalars and you're busting apart the plus signs. And it's all getting split up into these individual little terms. You see what I mean? And when I look at that expression, it starts to give me a hint about why linearity of a transformation is so useful, right? So let me give you an example. Maybe I'll give you a couple of examples of how you could use this remark to really understand a linear transformation more deeply. So let's assume that T goes from P2 of R to R squared is linear. Okay, so I want to assume now that I actually have a transformation that actually is already linear. We know, let's say we've already, for whatever reason, we have knowledge that this transformation is linear. Okay, and then let's say that if we are given that T of 1 is equal to 3 comma negative 5 and T of X is equal to 0 comma 8 and T of X squared is equal to negative 1 comma 4. If we are given those pieces of information, then I can ask you, what is T of anything? Right? Find T of any ax squared plus bx plus c. Like, we can actually reconstruct the entire transformation. The general formula for T of any quadratic polynomial if I just know these three things. This is the power of this. Let me just show you how it's going to work, guys. It's very easy. It's very easy. And you're going to have a couple of these to practice also on the next assignment. Basically, all you're going to do is you're going to look at this ax squared plus bx plus c, right? And you're going to use the idea from this remark, which is that if I'm transforming sort of an expression that looks like a linear combination of terms, I can bust it out. I can pull the a out in front and do T of x squared, right? And then I can bust out the b and do T of x. And then I can bust out this. If I bust out the c, then I'm left with T of 1. But I can definitely do that, right? This is because T respects linear combinations. So this is since T respects that expression, right? Linear combinations in general. T respects linear combinations. And now I can just plug in what I already was given, right? So this will be a times what? Negative 1 comma 4. And then plus b times 0 comma 8. And then plus c times T of 1, which was 3 comma negative 5. And there is your answer. You could actually leave it like that, but I'm going to go ahead and condense it back down now into just 2 slots. In the left slot, I see negative a plus 3c, comma, and then in the right slot, I see 4a plus 8b minus 5c. And that would be the formula. That would be the formula for it. Isn't that pretty cool? So just if we know what the transformation does to, by the way, this is a basis for P2 of R. If we know how T behaves on a whole bunch of basis vectors, we can use that information to write down what T will do to any other vector. I should point out, this has massive applications in computer science and particularly in computer graphics, because as it turns out, if you take a computer screen and you think about taking the pixels of this screen And let's say you would like to take an image and maybe rotate it, or maybe you want to flip it across an axis or something like that. Turns out that doing those kind of things, those are linear operations. When you rotate or flip or stretch a bunch of vectors in a plane. So if you know, for example, that when you do your transformation, that this pixel gets moved over here, and that this pixel gets moved over here. I'm just making something up here off the top of my head, right? So if you know that you're transferring, let's just say this is T of, I don't know, V1, sorry, no. This is V1. This is V1, and this is T of V1, and then let's say this is V2, and this is T of V2. If you know how this effect is applied on these two vectors specifically, you can then tell me, well, where does that point get moved to? And where does that vector get moved to? Because all of these other points, right, can be sort of expressed in terms of V1 and V2, right? Assuming V1 and V2 are a basis, right, then everything is expressible in terms of that basis. And so you'd be able to reconstruct the entire transformation, which might be some kind of an action on an image that is sitting on your computer screen. You could reconstruct that entire action from just knowing what happens to, say, a couple of points on your screen. Pretty remarkable. Same idea that we just showed here. If I tell you what T does to these three things only, and I don't tell you about any other points, you can figure out what T does to any other point by simply using this fact that T will respect that linear combination. It's a powerful idea, guys. It actually is also re-emphasizing the power of having a basis for a vector space, right? So if I know that 1x and x squared are a basis for P2 of R, that's awesome, because then everything in P2 of R can be written using that basis. And then T will respect that basis. It will respect any linear combination that you can build out of that basis. This is strong stuff. This is really, I mean, it's a big lift to have a transformation that's linear in the first place. But once you know that you have a linear transformation, you've got a lot of power in your hands to be able to say a lot about that transformation. So I think it's kind of nice to do that. And maybe I'll add one final remark here, and then I promise I'm going to stop for now and take a little break. But I'm kind of excited. I have a hard time stopping myself. I'm going to try to stop. I'll just make one last remark for the notes, and then I will try to calm down here. So here is the remark. If we have, say, V1 and V2 and ... up to Vn is a basis for V, and T, which goes, let's say, from V to W, is linear, then, so if we have a linear transformation from V to W and we write down a basis for V, then if we know the values T of V1, comma, T of V2, and ... up to T of Vn, if we know what the transformation will do to any individual basis vector. So if we know those values, so in other words, what I'm saying is these are given. If these are given values, we already know what they are, kind of like I gave you these values right here, right? Then in this case, we can compute T of any vector V. So you can compute T of V for any vector V from the vector space capital V. That's the big punchline. That's the big result of that. If I know what T does to a basis worth of vectors, then I can find out what t does to any other vector in the vector space. That's pretty dumb. And this is just one example to illustrate. Kind of gives you that idea. It's all because t will actually respect any linear combination, and every v, every one of these v's can be written as C1 V1 plus C2 V2 plus C3 V3 and so on, because we have a basis for v, a spanning set for v. Every vector in v can be written in terms of these guys. That's the idea. You guys don't look that impressed. That's okay. By Thursday, you probably will be, because I have some homework for you on this as well. So you're gonna get a chance to kind of think about how powerful that remark is as well. So anyway, I will leave it at that for now. Any questions about this? Last little bit here. If not, what I'd like to do is spend the last 15 minutes or so trying to help you with some of the homework that's due tonight, so that you can move right on into the next assignment pretty quickly. So I'm going to start with those problems that are on the board over there, since those seem to be in demand. And so we're going to change gears completely, of course, because this is back to chapter 5. So we're going back to the stuff on inner product spaces. Sort of part of my pledge, though, I give you guys a lot of homework to do, but I also try to do some of it for you and work on it and help make it a little easier on you. So let's take a look at 5.2 for starters, number 6. And this one has a vector v that they give you, which is, I think, 7, -2. And it says, it asks you to find all non-zero vectors w, so I'll just write it this way. Find all w not 0 in R2 such that the set consisting of v and w is orthogonal. Okay, so we're totally changing gears now. We've been talking about linear transformations all morning, and now suddenly I'm going back to inner product spaces again. Remember that two vectors are orthogonal if their inner product is 0. And in R2, remember that if we are working in Rn, the inner product that we're going to assume, in other words, the formula that we're going to assume here is just the regular dot product. So we're going to be working with just a dot product. For the solution to this, I'm just going to write my W with 2 slots. Okay, so this is pretty short. I'm just going to write my W. Maybe I'll write it as like A comma B. And I know that because it's in R2. It has 2 slots. And what I know is that when I dot W with V, I should get what? 0, because they're supposed to be orthogonal, right? The dot product should be 0. So let's just do that. Let's just do the inner product of V with W. Just using the regular dot product, that's just 7A minus 2B. And I just want to make sure that that is equal to 0. So I'm going to set that equal to 0 right now as a nice way to make this happen. And so what you end up with here, guys, is just a simple little equation for A and B. And this equation will have many solutions. Notice it says find all possible W vectors. So there's lots of them. One obvious answer would be 2, 7. If A is 2 and B is 7, then that's a solution. But you see, you have lots of other solutions too, because any multiple of 2, 7 would work as well. If you don't want to kind of wave your hands about this, you want to make it a little more precise, we can do that as well. I can set this up as a matrix, right? And I can basically say, all right, look, here's our matrix. We basically have a free variable. The B unknown would be free. I might call it T. And then based on that, I could solve for A. A would just be, 2/7 of T. So you can, by back substitution, if you solve for A, you'll just get 2/7 of B. And so what is my W then? My W is just the vector 2/7 of T comma, t. And the only thing is they said that w should not be 0, so you might want to just add the little note there that t is not 0 on that. But other than that, that's the answer to problem 6. Okay, so easy enough, right? That's kind of supposed to be the warm up for number 7. Number 7's a little bit, there's a little bit more to number 7. So let's look at the very next problem in that same section, which is number 7. It's a similar problem, but it's in R3 and there's a little bit more to it. So let me, are there any questions on this one though first? If you think of a question later, I hope you'll stop by my office and get it cleared up. Hopefully it's not anything too crazy, but I will definitely be around later for more questions. Let's look at number 7, which is also on the board over there. This time they give you the vector v. This one is going to be in R3, and this is the vector -3, 6, and 1. And what they want you to do is find all vectors that are orthogonal to v. Okay, so again, find all w in R3 such that v and w is orthogonal. So it's the same question as on number 6. And I would start off approaching it exactly the same way. So if you wanted to, if you were solving this, you probably would start this time with w being the vector ABC. We have to have 3 slots this time. And just like before, we would just dot that with the original vector v. And when I do that, when I dot the v with the w here, just using the regular dot product, we have -3a plus 6b plus c. And I'm once again, just like on number 6, I'm going to just set that equal to 0. We make this equation. And right, so by the way, what is this the equation of? Since it's in R3, maybe we have a chance of recognizing it from Math 250A. Yeah, it's going to be a plane, isn't it? It's actually an equation of a plane. It makes sense because if you imagine, I'm just going to draw you guys a little visual here. If you imagine v is this vector that they gave us here, and so here's this point, like what are all of the w's that are orthogonal to this vector? It's actually just going to be the plane that has this vector as its normal vector, right? You can actually, like if I took it one step further and I said, what is this the equation of? And you said it's a plane. Then my next question could be, well, what would be a normal vector for that plane? And the answer, as you probably remember in 250A, the answer is that the normal vector to the plane is just the vector created out of the coefficients of the unknowns. So -3, 6, and 1. That is the normal vector. Okay, so there you have it. So what they're asking us for here are what are all of these w's that are down here. There's a w, there's a w, all of these w's that are sitting down here in this plane. That's kind of what they're asking you to find. There's millions of them, right? Millions of vectors in that plane, infinite number actually. And they just want to know, well, what are all of those vectors? And we can just do it the same way that we did the problem 6. We can just make a little, one row Gaussian elimination problem. So -3, 6, 1, and augment that with 0, right? Just like the previous problem. And so here, you've got your A, B, and C that are kind of lined up with those columns. And we can just view the B and the C as free variables, right? Like we always do. I like to use R and T, as you've probably figured out by now, for free variables. So B and C are both free. B and C are both free, and then I just have to solve for A. So if I solve for A in terms of R and T, let's see, I think what we would get out of that is 2r plus 1/3 of t. I'm doing that without showing all my work. I'm just basically putting r right here and t right here and trying to solve it for a. I think I did it correctly. Okay, and so what are all of the W vectors then? Well, the W vectors would just be, first slot is 2r plus t over 3. Second slot is r. Third slot is t. So those are all of your W's. That's the first part of this question, is to find all of the possible W vectors that would be perpendicular to V. In other words, those are all of the vectors that are actually in the plane. Could we get a basis for this plane, by the way? And if so, how? Alex?
Use the Gram-Schmidt.
Gram-Schmidt is used to orthogonalize a basis. Here, I just want to get a basis for this plane. I'm wondering if anybody, that going back before we knew about inner products, if I asked you to find a basis for all of these vectors that are in the plane, what would you do? Wanna give it another try?
That's when you bust out.
There we go. Yeah, exactly. We're gonna bust out the variables here, right? So if I bust out the variables, you can see I'll get two vectors, right? Which makes sense because the plane is two-dimensional. If I bust out the r, I would get the vector 2, 1, 0. And if I bust out the t, I would get the vector 1/3, 0, 1. And you can check that both of these vectors are orthogonal to the original V. If you were to dot V with either one of these two vectors, you should get 0. There's no surprise in that. Now, there's a second part to this question, which it says, find an orthogonal basis for R3 that includes V. Okay. I'd like to explain that part, and then I might have to punt on some of that 5.3 stuff, but that's okay. Maybe I'll just make sure that I'm around my office hours, of course. But let's find an orthogonal basis for R3. By the way, if I stop right there and that's all I say, then of course everybody's answer is going to be, oh, I've got a very nice orthogonal basis for R3, which is just that. But this question is not that easy. This question is saying, find me an orthogonal basis for R3 that includes the vector V over there. So -3, 6, 1 is supposed to be one of the three. I know that any basis for R3 would use 3 vectors. And this is one of them. And we have to come up with 2 more basis vectors for R3 to add to this one, or to include with this one. Wondering if anybody has an idea how I could do that. How could I get 2 more basis vectors that I could throw in with V? Is that a hand, Angela?
Yeah.
What do you think?
If we do 2 more, then it matches the dimension. I would use independent. I think we use the original. Make sure that they don't cancel out and make a 0.
That's good points on all account. I do need more than just linear independence here, because I actually want to have an orthogonal basis. I got a lot of hands. I think Marco, you might have been first.
So we can just go ahead and, well, I just did error, just plugged in and saw it was what, but then once you find those vectors, you can multiply that with the original vector, and that equals 0.
Yeah, so we just said a moment ago, didn't we, that these 2 vectors, these are going to be 2 of these blue vectors that are on the plane, right? And each of these vectors is orthogonal to V, right? The only problem, so there's actually 2 ways to do the solution to this problem, by the way. The only problem is these 2 vectors are not orthogonal to each other yet. I agree that 210 is orthogonal to V and 1/301 is orthogonal to V. But if you dot these two vectors together, they're not orthogonal yet. So what would I need to do if I wanted to make them then? So let's say we take V, right? Let me give these names. Let's call this one W1 and I'll call this one W2. So I've got V and I've got W1 and I've got W2. It looks pretty good. That's the right number of vectors. The only problem is these two are not orthogonal yet. So what could I do? Johnson? The Gram-Schmidt process. Okay, so one way to do the problem. This is one, I'm going to give you two ways there, and you can pick your favorite one. One way to do the problem is to not worry about the V quite yet and use Gram-Schmidt just on these two vectors, which by the way, we probably shouldn't be calling them W's because in the Gram-Schmidt process, we would have called these, I'm so sorry, we would have called these V1 and V2. And then remember in the Gram-Schmidt process, you convert them into W1 and W2. Let me go back here. This is the trouble. I go different sections. So you could use the Gram-Schmidt process right here. So what that will do is you remember that the V1 just becomes the W1, and then there's a formula for the W2 that comes from the Gram-Schmidt process. I think I won't drag you through the details of that right now because I'm pretty much out of time. But there is a second solution. So that's one way to do it, which would be great. But you might be staring at me thinking, wait a minute, Gram-Schmidt, that was section 5.3. They shouldn't be asking us to do that here. This is only section 5.2. Did anybody think of another way to get this full basis worth of vectors that are all orthogonal to each other? Mohammed?
Do you get the cross product?
That's it. That is it. And that is not something we talk a lot about in 250B. But remember that when you take the cross product of two vectors, do you remember from calculus? If you cross two vectors together, the result of that is a vector that is perpendicular to both of the two vectors that you started with. So what you could do, guys, what you could do is you could take your first vector to be this one. This is the fast way to get the answer. That's your first vector. Your second vector could be either one of these other ones. Let's say 2, 1, 0. Now, so far, these two are perpendicular. How do I get a third one that's perpendicular to both of these? You could literally just take the cross product of those two vectors. So you have to remember how to do cross products. You guys remember the cross product thing? Believe it or not, you could imagine the cross product thing now like a determinant. Probably didn't do that in 250A, but you could think of it as a determinant, which means you're going to do some kind of a cofactor expansion on this 3x3. And I will let you guys check because I know we're out of time, but if you check this, I believe this is not looking right. Hold on a second. -1, the j component is 2, and the k component is -3 minus 12 is -15. Right? Yeah, that's great. That would be the third vector then. And so you just cross the first two together, you get a third one that works as a third base vector. Pretty cool, pretty cool. So I got through the 5.2 stuff. The 5.3 stuff, I will let you guys come to my office hours for. I'll be around a lot today. Feel free to stop by and I'll do my best to help you with that if you have questions on the Gram-Schmidt process. Thanks, guys.